This section is on infinite limits and vertical asymptotes. So first of all, some properties of infinite limits. If you take infinity, which is not really a number, but more of a, just a really infinitely large number, infinity plus or minus some finite number L, you get infinity. Infinity times a finite number L is infinity, and a finite number L divided by infinity, something finite over something huge, tends towards 0. Here's a quick limit. Limit as x approaches 3 of x plus 1 over x minus 3. This would be 3, this first part, but the second part is 1 over 0, goes towards infinity, so it does not exist. As far as the way this relates to asymptotes then, this is for vertical asymptotes. If you take a limit as x approaches c of f of x and you get plus or minus infinity, that's a vertical asymptote. And that's how, this is how it would look, this figure on the right. As x is approaching c, you're approaching positive infinity or negative infinity, so that's a vertical asymptote. Whereas, if you sort of flip these things around, take a limit as x approaches plus or minus infinity, that is x is going far to the right or far to the left, and you approach a finite number L, that's a horizontal asymptote, and we'll see that a couple chapters from now. So, a little bit more and then some examples. Now here's a rational function, and just to go through different aspects about this, you have to be careful when you cancel things out, how this would work. So if you cancel out x minus 1s, you have no more left on the bottom, but you did have one there before, so that would be a hole. It's not as if there's now suddenly a point there, so it would be an x-intercept, but there's a hole there. And you cancel over here, and there's still a couple left on the bottom. Because there's some left on the bottom, there's a vertical asymptote at -2. These cancel, and so that's going to be a hole and an x-intercept at x equals 3, because there's none left on the bottom, so it's a hole, not a vertical asymptote. Over here, this doesn't cancel with anything, so that's a vertical asymptote at -4. And finally, up top, that's just a 0 of your function. If you plug in 4, you get 0 for the numerator, so 0 for the function. So a few more examples here. In this problem, the idea was to find all vertical asymptotes of the function f of x. And so one way to think about it is secant is 1 over cosine. So if you want to find vertical asymptotes, you can see where the denominator is equal to 0. So where is cosine pi x equal to 0? Well, we could say then that pi x is equal to plus or minus pi over 2, plus or minus 3 pi over 2, and so on, because cosine is equal to 0 at these spots. But we want to get x, not pi x, so we divide everything by pi. And so our solution for vertical asymptotes would be all of these. In this problem, you're supposed to think about what's happening as x approaches -1. As x approaches -1. Now, if you just plug in -1, you get sine 0 over 0, and so that's indeterminate. So we're really looking to try to solve this limit. Now, one way to do it is to think of making a variable substitution. You imagine that theta is equal to x plus 1, and so now you've got the limit as theta approaches 0 of sine theta over theta, which we know is 1 from the squeeze theorem. And graphically, what this looks like is the function sine x over x, but shifted 1 to the left. This is another problem involving infinite limits. As we approach 1 from above, or from higher numbers or from the right, we plug it in up top and we'll basically get 3, or close enough to it. And on the bottom, we have 1 minus something a little bit bigger than 1. And so that's going to be negative, but very, very small. And so finite divided by very, very small is very, very big, and you have that negative, so it's negative infinity. Now for this one, you plug in 0 to the first limit, and that's 0 squared minus. We've got a 1 on top, plug in 0 for the second one, but it's coming from the left, so you're negative and very, very small. And so now we have 0 squared is 0, minus, and then these negatives will cancel. 1 divided by something very small is something very, very big. So 0 minus negative infinity, so it's just positive infinity. And over here, we want to find the limit as x approaches 3 from above. It's important to think about which direction you're approaching, because if we look at the unit circle over here, what we see is we're approaching, basically we're approaching pi over 2. If you plug in 3, you get 3 pi over 6, which is pi over 2. So you're approaching the top of your unit circle from bigger angles. And so as you're doing that, your cosine is going to be negative, not positive, but negative, because you're coming from quadrant 2. And secant is 1 over cosine, and so you have 1 over something negative and very, very small, which is why you end up with negative infinity. Now if we look at the graph of this function, we would see that over here, and basically we're coming along this portion of the curve going down towards negative infinity.